and record. All right, so let me first begin by making a brief recapitulation of the last lecture. We started discussing QFT in curved spacetime, and the first thing we talked is what is QFT in curved spacetime. It is when you describe quantum fields evolving on a fixed background, not necessarily curved, but usually curved. For these fixed backgrounds, we chose a specific class that is particularly convenient, those that are globally hyperbolic. Globally hyperbolic means that we can solve classical initial value problems, essentially. Furthermore, we also started studying the algebraic approach, where observables constitute a star algebra curly A, which is a C vector space has an associative product dot, which goes from AA to A, and has an involution star from A to A, such that A star star equals A, and AB star equals B star A star, where this is the dot product. Meanwhile, states, I didn't mention this last time, but I should have, are functionals linear functionals. Omega from A to C such that omega of the identity equals 1 in omega of a positive operator is positive, where a positive operator is an operator like this one that can be written as A star A. Okay? Does this make sense for you, for everyone, that this represents a notion of a state? So it is similar to how I could do in a Hilbert space, something like this. This is normalization, and this is so the state is positive, as we would have with this sort of sandwiches. Okay, I'm assuming everyone is comfortable with this. So our goal for today in quantum theory, is a theory such that the algebra A is not commutative. Our goal for today is find A such that the Klein-Gordon equation makes sense and is respected, and such that A is not commutative. To do so, we start guessing. This is the approach taken in a paper by Holland and Wald. In 2015. The main objects of this algebra make sense to be phi of x in principle. So the field configuration is phi of x. Due to some issues with distributions, so I want to avoid dealing with delta of x, for example, we're going to work not with phi of x, but rather with smeared fields, which are phi of x integrated against some f of x, which is an arbitrary function, u for x. This could work also for dpx in arbitrary dimensions, but I'm going to focus in 4 dimensions there. So we are going to use these as the basic objects of our algebra. We should be able to somehow sum these objects and multiply them by scalars. So if I have an expression like this, I'm going to impose, based on this equation, that these fields obey f plus lambda g. This way I impose linearity conditions so that I know how to sum and how to perform multiplication by scalars in the algebra. So I do have a vector space. I can also, of course, multiply these guys, and there are going to be objects in the algebra corresponding to these multiplications. So far, so good. This is a bit abstract, so feel free to interrupt me if you need.
Sorry, but you don't want to work with bounded operators? So phi of f by itself is not bounded, right?
Yeah, I don't necessarily need to work with bounded. It is useful to work with bounded operators, in which case we get a C-star algebra instead of a star algebra. But it is possible to also work with star algebras, which are a bit more difficult to deal with from a mathematical aspect, but I find them easier to understand from a physical perspective.
Okay.
Okay.
So, yeah, okay, maybe we'll talk about it later. Yeah.
It is possible to, yes.
There's a comment asking you to redo the motivation for using smeared functions again.
Okay. I'll get to a better argument later on when we are discussing why exactly we need smeared functions. It comes when you work with the commutator. And then you force the algebra to not be commutative, and you need smeared functions when you get there. So I think it would be best to wait a little bit, and this will become clear in due time. If it doesn't, feel free to interrupt me. Okay? But the reason is because eventually we will see. Oops.
Someone is asking about the difference between the C-star algebra and just a star algebra.
Oh, okay. Let me just reshare my screen. The app closed suddenly. A C-star algebra has a norm. So we are working with operators, with observables, such that you always have a norm and they are bounded. So they are smaller than infinity, smaller than 3. Star algebras do not have a norm. They are more general in the sense, so all C-star algebras are star algebras, but in a star algebra you can have something, some operator that in some sense because it does not have a norm. But if you try to put a norm in there, it might be that some of those operators are infinite. So for example, if you pick position, the norm of position, which would be, I think the highest eigenvalue. Yeah, that's an example. For example, define the norm such that it is the largest eigenvalue. Or I'm not really sure that is a norm, but I think it might be. As a sake of example, take that. So for position, this would be infinity. Okay, it's difficult to write now. Let's keep trying. Let me use Zoom's whiteboard because I think it might be a bit better. So for a C-star algebra, you have a norm and all operators have this norm is smaller than infinity, while the star algebra could contain, for example, the position operator. This in regular quantum mechanics, not in quantum field theory. And this has infinite norms because it has infinite eigenvalues. So it is more convenient from a mathematical point of view to work with C-star algebras. However, in physics, we usually work with star algebras instead of C-star. In the mathematical literature, when you read books on algebraic quantum field theory, right, QFT, they typically prefer to work with C-star algebras. There is one exception, which is a work by Cavicini and Morici. I'm not really sure how to pronounce it in Italian. I think it's 2015 as well. And they work with star algebras. It is mathematically a little less convenient, but it is more intuitive from the point of view of a physicist. In my opinion, at least, and in theirs as well. Does this explain?
Yes, thank you.
You're welcome.
Can I ask you a question? So the curly A, how should I understand it? Should I understand it as the algebra of observables, or should I understand it as the all possible operators you can define in your theory?
What was the first possibility?
The curly A that you wrote down in the previous slides. So should I understand it as the algebra of observables for the theory, or all possible operators that I can define on the theory?
All possible operators.
Okay.
So let me give you an example. Suppose you have a Hilbert space, H. Then the algebra A can be realized. Oops. as the linear operator is acting on H. So all operators A that go from H to H. In this case,
But
H
the
will be,
unbounded operators need not be defined on the full Hilbert space, right?
sorry?
Uh,
Yeah,
so
unbounded
the unbound,
operators. Yes, indeed. But I'm thinking here of an unbounded operator defined in a dense domain, for example, or
okay,
something like that.
okay, thanks.
You're welcome. Okay, so where were we? We'll try one more time to use the other blackboard, because it is way more convenient. And okay, so we have this vector space to work with. We have this algebra product. We now want to introduce a star from A to A. To do so, we're going to see that phi of f star should be equal to phi x conjugate f of x conjugate square root of g ddx or d for x. For a real field, this means we get phi of x f of x conjugate minus g d for x, and hence we get to phi of f bar. So we impose this on the algebra as well. This is the condition that the field is real. We could also work with a complex Klein-Gordon field, but that would be more complicated. Similarly, we could work with higher spins, but it also would be more complicated. So we're sticking with the Klein-Gordon equation, or the real Klein-Gordon equation, simply because it is easier to work with. Okay, and finally, we must make this algebra non-commutative. Typically, the way we do this in regular quantity theory would be to impose that at the same time, phi and phi somewhere else commute. The delta t phi and delta t phi somewhere else. Sorry, this is zero. This is zero. Also commute. Let phi tx and dt phi ty are such that, let me just remember what is the correct sign. I delta 3 x y times z and z. So these are the canonical commutation relations. Notice that I have a delta on the right hand side. So over here I have a delta. Since I have a delta and I'm just multiplying operators together, they cannot be regular functions. They must be distributions in order for me to get a distribution with the commutator. Does this make sense? Does this answer that earlier question? I'll give you a little time to think. If this were both regular functions, it would be impossible for the commutator to be something like this.
Dominic says yes.
Okay, thank you. And okay, so we have this. Now, there is a convenient manner to write this down, which is the following. In a globally hyperbolic spacetime, we can find some convenient green functions. So a green function is a function such that gx prime equals to 1 over square root of g dx prime. Is this a convention I use in my notes? Yes, it is. Such a function, actually a distribution, is convenient because if I have gj of x defined as g x prime j x prime square root of g e for x, then I find that applying the Klein-Gordon operator to gj will lead me to 1 over square root delta x prime, because I apply the Klein-Gordon operator to this g in here, jx to g e for x prime. Using this direct delta, what we get then is simply this g cancels with this g, and we use the remaining direct delta to get j of x. Hence, having a Green's function lets you find solutions to the Klein-Gordon operator, to the Klein-Gordon equation, with some arbitrary source j. In particular, in a globally hyperbolic spacetime, we can find two interesting Green's functions, which are the advanced and the retarded Green's function. To describe them, let me first mention that the causal future of some set S is given by all points such that there is a time-like or light-like curve lambda such that lambda 0 is on S and lambda 1 equals the point P. So it is, for example, I have some surface in here, and this region is J plus S. This is because I can always find curves that go to each of these points causally. So this is the general relativity equivalent of the future light cone. Does this make sense to everyone?
Here, S could be any set in the spacetime, like any region in the spacetime.
Yes, it could be any set.
Okay, so it may not be restricted to a Cauchy surface, is it?
Sorry?
I mean, I don't have to consider a Cauchy surface and then a subregion inside the Cauchy surface to consider this.
No. And similarly, yeah, sorry, I should have added something like. Come on. Yeah, we're going slowly today. But getting the hang of just starting it fast. There's this star that I forgot to write, which is future directed. So lambda 1 must come after lambda 0. Similarly, we can define the causal past, which is just going to be this different region that goes to the past. And I can reach it by going back in time. All these curves are causal. So J plus S, yeah, this is J. Yeah, this is difficult. Let me go back to the whiteboard. So this is J plus S. This is J minus S. J plus S is the set of all spacetime points that can be affected by S, while J minus S is the set of all spacetime points that can affect S. Now, something we can find concerning Green's functions is the following. Oh yeah, we define the support of function sub f as the region where f is not 0. This is the mathematics convention. The physics convention sometimes includes topological closure, but I don't find it necessary in here. So it is the region where the function doesn't vanish. We can now pick no, this is too high. G plus to be the Green's function such that the support of G plus J is within the causal future of sub J. So I have here sub J and sub G plus J is in here. And similarly, we define with the negative sign. So sub G minus J is in here. So you see, G plus is called the retarded Green's function. It picks the information on the support of J and brings it to the future, while the G minus is the advanced Green's function. It picks the information at sub J and brings it to the past. Okay, does that make sense? This is quite similar to what happens in electrodynamics, by the way. So in electrodynamics, you sometimes find the retarded and the advanced Green's function. These are the same ideas.
Nick, what is the meaning of the sub notation again? I forgot.
Yes, a sub of f is the set where f is not 0. Does this make sense? I just write this in a very informal way. I can write the proper definition. Let me. Sup of f equals the set x in the manifold such that f of x is not 0. So it is the region where the function doesn't vanish. So all the information that J gives is within this region sub J. All of the data that J gives is within this region. Now G plus propagates that information to the future, to within the causal future, while G minus propagates that information to the causal past G minus. Does that make sense?
Yeah, makes sense. So usually you'll not use this, for example, sub of G on the infinities, like the infinities of the manifold.
No, I'm mostly concerned with functions that are of compact support, which means the support does not reach infinity.
Okay.
You are usually interested in functions such like this. So a function such as e of x, e to the x, it has infinite support. It is supported everywhere. So it gets somewhat more complicated. In QFTCS, we often focus on functions that have compact support. This is because distributions are defined with functions of compact support. So in order for those equations such as phi of x against f of x dx to give a finite value, we require that f of x has only support in a compact region, so that the integral goes to 0 at infinity. Does this make sense?
Yeah, makes sense. Thanks.
You're welcome. This is very common in the Fourier distributions. Let me clear everything. We
Now, maybe you
define.
could add a whiteboard, bottom right corner, instead of erasing everything.
Oh, okay, I can add a new one here. Thank you. All right. So we can also define an E green function, sort of a green function, that is given by G plus minus G minus. It has interesting properties that delta E dt x t prime x prime. Is this the correct expression? Yes. At t equals t prime equals minus dx x prime. And E t x t x prime equals 0. This one can be seen by a more complicated calculation. This one is straightforward because it is given, again, by these guys over here. If we just pick spatially related things to the support of J, it is going to vanish. And here we are picking exactly spatially related points. So what we get is X is this point, for example. When I pick this different point here at the same time, it is going to vanish because the support is within here. I'm just not able to add. Okay. And this is interesting because we are then able to write all those commutation relations in a simpler way. The phi of x prime equals I e of x prime identity. So this summarizes
Nick,
all of the, yes.
there's a question in chat from Etelali, and she asks, what changes if S is light-like? Because then the Green's functions would give evolution along S. Should we be careful of something then, or is the story the same?
What happens if
I
it's
guess
light?
it was when I guess it was when you were discussing the Green's functions.
I don't see anything difficult when it is light-like. The G plus J might appear on the light-like region and might not. It is not forbidden, not an issue. Does it make sense?
Yep.
Okay. So we are dealing with this. Since this is the covariant version of the canonical commutation relations. And since we are dealing with distributions, we can just integrate everything against functions f and g. Similarly here, f and g. And we get to the actual commutation relation we are going to impose on the algebra.
Nick, there's a question.
Please.
Does light-like behavior corresponds to ghosts and tachyons?
No. Tachyons would be if you had something moving faster than light, which means space-like behavior. And we don't have that here. From the start, we are building everything up in a way in which you don't have tachyons. While ghosts are a completely different thing. It depends a bit on what you mean. These are typically non-physical degrees of freedom. So you might have ghosts that are not that scary, such as the ones that appear in gauge theory, and those will be treated just as well in here, in the same way I'm doing. Or you can have ghosts that are what happened, for example, in the, what's the name of the theorem? That happens when you have higher derivatives in the Lagrangian. Ostragradsky's theorem. I think that's it. In which
He
case,
corrected himself, saying that it's for space-like, and he says that he thinks that it should be at least for the space-like part of the wave function.
yeah, let me open the chat to
Okay.
read it. Ooh. Oh no, we don't have a space-like behavior in here. We just cut it off from the start. Ghosts would be if you had something different, such as higher derivatives, in which case, higher derivatives of interaction, in which case you might end up with negative energy particles, where I use the quotation marks because we'll see that the notion of particle is quite subtle within QFTCS. Okay, so is there anything else I'm missing? So with this, we get to the full algebra. So the first rule is that phi of f plus lambda phi of g equals phi of f plus lambda g. The second rule is that phi. Oh yes, I forgot to mention this rule, which is a particularly important one. We want to impose that the field solves the Klein-Gordon equations. So in order to do that, we notice that we can start with this. Which equals, through integration by parts, this. We know that if we want phi to be a solution to the Klein-Gordon equation, we want the first equation to vanish. So this is 0, while this one here is phi of the Klein-Gordon operator applied on f. So this is the final rule we wanted in order to keep this being a theory about the Klein-Gordon field. Hence we get
Sorry,
4 rules.
what were you trying to do? So phi of x, f of x was a smeared operator, right? Or the smeared
Yes.
field.
Yes.
And you want to see the action of the Klein-Gordon operator on the smeared field. Is that what you're trying to do?
Yes. I want this field to somehow solve the Klein-Gordon equation. Within distribution theory, this is equivalent to imposing that phi of the Klein-Gordon operation times any function should be equal to 0. So phi of x solves the Klein-Gordon operator. The
Right.
Klein-Gordon equation. Does that make sense?
Yes, and but then how could you throw away the boundary terms? What conditions are you assuming to throw away the boundary terms?
We're assuming that f of x has compact support, so it has support in some region over here. But when you get to a certain distance, it is 0.
No, but here I think the boundary condition has to be imposed on the derivative of f, right? Not on f itself.
That is a fair argument, but since f is going to vanish out here in this region, this large region, the derivative of f in here is also 0.
Okay.
Does it make sense?
Yeah. Okay. That's good.
So we got to the 4 rules that define our algebra A. One is that phi of f plus lambda phi of g equals phi of f plus lambda g. This ensures that the algebra is a vector space. We also can take as many products as we want. Phi of z or something. Or let me write this differently. F1, F2, Fn, they all belong in the algebra. 3, the Klein-Gordon equation is solved by the field. 4, the field is real. And 5, the commutator relation. Okay, so this is the algebra for the quantum Klein-Gordon field on an arbitrary spacetime. So right now we have quantized the Klein-Gordon field in a curved spacetime by just giving this algebra. We can later, as we shall do in the next lecture, we can pick this algebra and find a Hilbert space for it upon some more extra considerations that are valid in some interesting spacetimes, but not in all spacetimes. Okay?
So to begin with, you're working with the particular choice of time, right? But there is a general covariance, there always a possibility of redefinition of what the time coordinate is.
Yes,
So how is that thing? Sorry.
I'm not actually making any choice of a preferred time in here, because at first I did use a preferred choice of time in order to write the commutation relations, but this
Yes,
version
the
here
final.
makes no reference.
Okay. Okay. So, sorry, could you please repeat? How should I understand EFG again?
EFG.
Yeah, the last, the right-hand side of equation 5.
Huh? Let me just see if it is written somewhere here. Here. EFG is equal to the integral of E x prime, which is a bidistribution, times f of x, g of x prime here, right here, square root of minus g, d for x. Yeah, these two g's are different, so let me perhaps write EFH.
Shouldn't it be a double integral over d for x and d for x prime?
Oh yes, indeed. Sorry.
Nick, there are a few questions in the chat, so when you are available, you just tell me and I'll read them for you.
So on the left-hand side of the, sorry, can I continue? So in the first
Please.
equation that you've written on this slide, what is the subscript in the left-hand side? So the phi of x prime commutator is there, and then you have the something more you have, right? So that should also be a double integral on the
Yes,
left-hand side of the topmost.
Yes, this is a double integral. And this is a double integral that just ran out of space.
Okay, so basically you're expanding the phi of f and phi of g and writing it out.
Yes, I'm smearing the phi of x and the phi of g, the phi of x and the
Right.
phi of x prime to become phi of f and phi of g.
Okay. Thanks.
Okay, you're welcome.
Thanks.
The smearing makes the field non-local. Means how do you maintain local covariance? Let me think a while. This smearing is actually only a mathematical aspect. It is just so that we are working with well-defined operators instead of distributions. The difference is that instead of writing delta x for the direct distribution, I'm writing all this delta x applied to some function which is going to be f of 0 dx integral. So actually, you can also think that I'm working with phi of x. It is not really. It is more or less necessary to work with the smeared operators. because they are distributions, so they are similar to the Dirac delta, but this is still locally covariant. I'm not sure whether that answers. There are some other you're welcome. There are some other more complex ways of discussing this, which I'm not completely familiar with, but there is something called locally covariant quantum field theory, which is a more mathematically complicated approach to this, in which you use categories to ensure everything is covariant in the same way you would expect it. It is somewhat more complicated. I don't know much about it. I think the only book I can recommend about it that I know by on the top of my head would be Perturbative Algebraic QFT by Kasia Reisner. Let me write this on the next slide.
Hi, I've got a
Yes.
doubt. The 5 equations that you had written in the last slide, those define the space of operators that solve the Klein-Gordon equation. Is that right?
Yes, it is a space of observables for the quantized Klein-Gordon equation. It also
Okay.
includes these products that are a bit more complicated.
Okay. Okay. Thanks.
You're welcome. Let me see, there was one more question in the chat.
Nick, there are 2 questions by the same person. The first one is the algebra abelian? And the second one is, in the interactive theories, the property of Euler-Lagrange equation cease to be valid?
Yeah, the algebra is not abelian because I'm imposed this commutation relations down here. So actually, when you have 2 operators, you are going to have these commutation relations, which are the canonical commutation relations written in a covariant form. As for the property of Euler-Lagrange equation cease to be valid, I'm not really sure what you meant, but something I should add in here is that we're doing free field theory. To do interactive field theory, it is much more complicated, way more complicated. So I'm assuming we're only dealing with free fields in this course. Does this answer your question?
He says that he meant property 3 of the Euler-Lagrange equations, I
Oh,
think.
I see. Yeah, I'd say that these are the Euler-Lagrange equations for the case we are considering. So if you were to consider a different theory, you would need to modify step 3 to your preferred theory. But this is for free fields. If you were to do interacting fields, things get way more complicated. And an introduction to that is found in this book by Reisner that I haven't read yet. So it is ahead of me in particular. So we're going to focus in free fields. Are any more questions?
There is another question. Why do you call these why do you call these observations? Wouldn't those of the fields instead of the abstract.
Sorry, I didn't understand what you said.
There are two questions. The first one is, how do you call these observables? And then he continued, wouldn't the endpoint functions of the fields instead of mutings?
Not exactly. We still haven't got to endpoint functions. But
I think Rob is worried that it must be used to thinking of endpoint functions as instead of as mirrored to functions.
yes, I'm going to get to endpoint functions in a second. So we can use these observables in a state to get the endpoint functions. But you need a state in order for you to have endpoint functions. So the observables are one thing, the states are another thing. When you bring those two together, you can get endpoint functions. But this is an important difference that occurs in curved spacetime, because when you're doing with flat spacetime, you have a preferred state, which is the vacuum. But in curved spacetime, you don't have one vacuum. You can have many different vacua, and you have to choose which is the particular state you're working with. So it gets a little bit more complicated. Um, answering the question
Going
about
back
quite
to
tree.
the question before that. Oh, okay.
Yeah,
Okay.
I'm
You've
reading.
already read.
Yes. Um, um, I am guessing, but I would say that you still require the distribution satisfy P3, but you're going to correct it perturbatively. We have, as far as I know, we have no idea how to do this non-perturbatively. We don't know what is a quantum field theory in a non-perturbative manner, to the best of my knowledge. It is in particular one of my favorite questions in physics. You're welcome. Okay. So unless there are any more questions, I'm going to proceed. We have now constructed the algebra and the other side, so we have observables, and the question is now, what are the states that we have? So states are, it is not trivial to find states in an actual algebra, so it is typically easy to construct the algebra. It is typically hard to find rigorously defined states on it. So I'm going to overlook those difficulties and just do things formally and describing formally what are some possible states that we are interested in a few cases without diving too deep into the details of whether they are rigorously constructed or anything like that. Although I do think that the states I'm going to mention are rigorously constructed nowadays. So the first sort of interesting state would be what we call a vacuum. That's when we define endpoint functions. So I'm defining endpoint functions in a smeared way, which is going to be omega of phi f1 until phi fn. You could, of course, also work with n distributions, which would be phi of x1 to xn and omega of phi of x1 to specify effects then. I think this is the most common approach when we're doing when we're making QFT rigors with the Whiteman axioms. But in the algebraic approach, it is more convenient and usual to work with these mirrored versions. So notice this depends on a choice of state. So omega here is a choice of state. And on different states, I can have different endpoint functions. Now, one particular property of the Minkowski vacuum is that it satisfies the following. For 2n plus 1, well, let me just take my copy here. So 2n minus 1. The 2n minus 1 endpoint functions vanish, while the 2n endpoint functions are given by a set of pairings of 2 by 2 point functions. This is called Dick's theorem. So in a general curved spacetime, I expect the vacuum to also have this property. This is what we call a Gaussian state. So I want a vacuum to be a Gaussian state. Okay? I'm
Sorry,
just mimicking.
why is the first equation zero? Like the odd point functions to the zero? Like
Yes, we are dealing with free field theory.
also. Okay.
Okay?
I would have agreed if instead of smearing the functions, we had like odd number of insertion at space-time points. But now that we have smeared the fields, should we expect this to hold? Like if we had omega acting on like phi of x1 up to phi of x2 n minus 1, then by parity we can argue it to be 0. But now that there's a smearing going on, should it still hold? Why should it still hold?
Yes, because let me. We would have something like this. Then we integrate against, for example, f1.
I see. Okay.
2n minus 1. And since the integral is 0, this is also going to be 0.
Okay, yeah, that makes sense. Nice. Yeah.
You're welcome. So we want vacua to be Gaussian states. Furthermore, we are also going to ask them to be pure. Because the Minkowski vacuum is pure, and also it makes the description easier later on. This is the definition of a vacuum in curved spacetime. It's a Gaussian state that is pure. Gaussian states are also called quasi-free states. So this is what we call a vacuum. The reason we mentioning about vacua in the plural is because here is how we define the Minkowski vacuum in Minkowski spacetime. Either it is 0m minimizes the Hamiltonian. Now, Hamiltonian is energy. Energy, by Nieder's theorem, is a charge conserved through time translation symmetry. If we have time translation symmetry, excellent, we have a Hamiltonian. However, in the general curved spacetime, we don't have time translation symmetry. For example, in our spacetime, things expand. In an expanding universe, you don't have time translation symmetry, and hence you don't have a Hamiltonian. And hence, you can't really say that a vacuum is that which minimizes the Hamiltonian. Alternatively, it is the only Poincare invariant state, which means nothing in curved spacetime because we don't have Poincare symmetry. Hence, the two usual characteristics of the Minkowski spacetime do not apply when you're doing QFTCS, and you have to find new ways of defining it. Hence why we use Gaussian pure states. Does this make sense?
But sorry, I have a small question.
Mhm.
Couldn't you work at the locally flat frame so you could actually use the second condition, for example, even in curved spacetimes?
Not really, because the vacuum is a global aspect.
Okay, fair.
So that does this make sense? This affirmation that the vacuum, that the state is global.
I'm not
Because-
sure why it has to be global necessarily, but if we take it so, then okay.
Yeah, it's because when I want a vacuum to be something that I ask, what is the expectation value of phi of f phi g? It might happen that f and g are completely separated in the spacetime. So maybe this is the support of f, this is the support of g, and the vacuum has to know about both of them.
Okay. Yeah, okay, it makes a bit more sense now.
But isn't this true for any state? Like, so we have to define it on a full space-time slice, right? And using the usual path integral formalism. Like when we define states, we define it for the full slice of the space-time.
Yes, you are defining an entire slice of spacetime. That is the point. It is global. This works for
Yeah,
any
but-
state, not only the vacuum.
Yeah, okay.
Okay. I think I'm going to stop the class here because it's starting to get quite tiresome. And what comes next is also quite tiresome. We still have to discuss a little bit about thermal states, Hadamard states, and a bunch of effects. So I think it's a good place to stop just after defining vacuum. Are there any questions you want to ask now?
There is one question in the chat.
Okay.
Inquiring if, since we don't have a global vacuum, does that imply non-locality?
Not really. You actually you have a global vacuum, and in quantum field theory you do have some non-local features. So, for example, when I pick the 2-point function, I do have correlations between space-like related regions, for example. So it is intrinsically non-local. You always have this relations between different regions in curved spacetime, this entanglement between different regions. So it is a little bit non-local, but not non. I would say it means nothing because the vacuum, the state, is a global construction. You can throw away information, so you can integrate out or trace out the pieces of the state and get information only about a smaller region, but still it is always global. So it is always global within that region you're looking at. You cannot just pick a local vacuum, a local state. The support of the functions does not need to be connected. It needs to be compact. You're welcome. You're welcome. So, anything else?
I have a question.
Please.
Right now we've covered the smearing of the fields with functions of compact support, right?
Yes.
I guess this might be covered later, but usually in QFT we work with Fock states, and my question would be if when we work with Fock states, would this mirror would this mirror be in a sense substituted by a Fock state, or is it completely different?
No, when we work with Fock spaces, we are going
Because
to
you
find that the algebra can be represented as the operators on a Fock space.
okay, because
So,
usually the fields are applied to Fock states, right? At least in normal QFT, no? Mm-hmm.
yeah, that is a choice of representation of the algebra.
Okay.
So you can, just like you can represent groups on a Hilbert space by, you pick an element of the group and you write it as a matrix, you can represent algebras by writing them as operators on a Hilbert space.
Oh,
Does
okay.
it make sense?
Yeah. So, but in this formalism of QFT curved spacetime, would that mean that if we wanted to use Fock states in order to work with this framework, it is a matter of choosing the representation of the algebra, right? Like you said?
Yes.
Okay.
So
Okay,
you,
thank
you choose a preferred vacuum that you want to work as the vacuum that is annihilated by all annihilation operators in your Fock space.
Yeah.
And then you can find a Fock space in which that one is the vacuum, but it is dependent on your choice of vacuum. So which state you chose to make the representation.
Okay. Thank you.
Okay, you're welcome.
Yeah, thank you.
Sorry, could you just go over what is the definition of vacuum? So it's the minimal state, minimal energy state, and it requires Poincare invariance. Is that the two criteria you're demanding?
No, that is the criteria in Minkowski spacetime.
Okay. For a generic spacetime, what do you require?
For general spacetime, I require them to be Gaussian, so Wick's theorem applies, and to be pure.
So how should I understand the pure here? Like, is it the usual quantum mechanical pure state or something else?
Yes, it's the usual quantum mechanical pure state.
Okay, good. Thanks.
You're welcome. Okay, anything else?
There is a question about, by choosing Gaussian states, are we working with coherent states only?
I guess so, in a certain sense. We focus on Gaussian states because they are more interesting to us usually. And I see Gaussian as being coherent with, I mean, it has eigenvalue of 0 for the annihilation operator, so in some sense, yes. But also in QFT, in regular space, I mean, we work only with a vacuum, which is also the same case. So, in fact, in curved spacetime, we have more options than in flat spacetime. So, by choosing Gaussian states, we are just replacing the role that the Minkowski vacuum plays with something else that applies in curved spacetime. Does it make sense? Okay, any other questions? Oh, okay. Did you hear what I said? Oh, all right. We are essentially replacing the Minkowski vacuum that we usually use in QFT and flat spacetime with some other sort of vacuum that is going to play its role in curved spacetime. So you can, in principle, apply creation operators to have a more complex state, and it works just as in flat spacetime. At least when you're using a Fock representation. Okay. You're welcome. Anything else? All right, I think we'll stop here then. And in case you have any questions, you can email me or you can ask me at the beginning of next class. And I'll make this recording available as soon as possible at the same folder you received through email for the previous one. Okay.
Thank you.
Thank you very much
Goodbye.
for your presence. Bye-bye.
Thank you.